So today we will run for 1 hour or 1 hour 15 minutes, and possibly we will cover it up in the next session. I mean, we can extend the number of sessions also, should not be a problem. So we'll go ahead until 9:15 or so, and possibly 9:15, 9:30, and then we'll try to stop it. We'll add it somewhere else, not an issue. Right? Possibly it's the entire syllabus to be getting over. Probably a couple of extra days may not be a big difficulty. Okay, so quickly before we actually get into the modeling aspects, I want to quickly summarize upon what all you can play with your data. What are the various plays that you can do? What are the initial things that you would work on, which we typically call as exploratory data analysis? Of course, I'm talking about the basic exploratory data analysis. Given any data for you, of course, some of the things we have already done while discussing about the pandas or while discussing about seaborn or something, but the intention is to just aggregate all of them. So one data being given to us, what is the flow, right? So if you look at it, this is what is a kind of a structured flow that you can see. Now you know pandas, you know NumPy, you know seaborn, you know matplotlib. So how are we integrating all these things into what is called as exploratory data analysis? We are exploring the data, right? So you import all your necessary libraries, especially NumPy, pandas, seaborn, matplotlib. In some cases, possibly you may want to look at the stats models as well, and SciPy also. So these are two different libraries which give you a little bit of, right? So basically, when I'm a little bit of additional statistical related aspects and some computing related aspects. What is import warnings? So basically, for a lot of these messages, there are the messages that you get out of the code. You have a lot of warning messages, you have a lot of error messages, you have. So when these programmers, they classify different kinds of messages, they put some messages under the category of warning. They will not be errors, but they just kind of give you possibly this is not compatible with this version of pandas, or possibly NumPy, the current version of NumPy is this, so I mean basically saying this was compiled in this version of Python, this was compiled in a previous version of Python. Some such kind of messages could be there, or in some cases these programmers, they will write some set of lines to print out just as a kind of flow, log messages kind of thing. So what we generally say is, probably all these kinds of warning messages that come out, let's ignore them, because otherwise in my notebook, I'll see many such kind of outputs, and possibly the actual error messages could not be noticed that easily. So that is where we say, especially when we are writing so big a kind of models, we say let's better ignore the warning messages. They do not impact our output. Possibly that is one of the reasons. So these all become a kind of very standard kind of a template. Now, just to observe the data, go with this section. Maximum columns set to none, maximum rows set to none, so that the entire data can be seen wherever required. Otherwise, ... some number of columns, only the first few columns and the last few columns will be displayed. We have discussed about it. Then here I am also talking about a mechanism where if you want to upload, see, till now we have looked at uploading the data from the Google Drive. But let's say if I have my data already in my file system, so I can upload it through this mechanism. So from Google.colab, earlier when we are doing from Google Drive, we were saying import drive. Then we were saying drive.mount, and we are giving the location of where the drive is mounted. Whereas here we are saying files.upload, and you can, once you run it, you will get a choose file. You can go through your file system, C, D folders, and based on that, you can select the file on your system. Then it gets uploaded. So this is a way to upload the data into the Google Drive. Into the Python environment or into the Colab environment, if it is in your local file system. So we are reading it. Quickly I'll go through, because only where there is an importance we'll spend time. I'll look at the number of rows and number of columns on the data. Quickly look at the top n observations, the bottom n observations, or if you want randomly check some number of observations. This is just to see, get a fair amount of what is the data all about. How many variables are there? What is the kind of type of the data, type of the variables, etc. Just get a hold of what kind of data is there. Then look at the columns, right? The intention of this is, if at all some columns required to be renamed, you can very well do the renaming of the columns. As we have seen here, some column names are renamed. So if you want to rename, better do it. I'm just giving it as a structured flow. Then look at the info function. See how many missing values are there. If any data types required to be changed. So you would be typically focusing on those aspects. Right? Are all the data types pretty much fine, or do they require to be changed? Now here, let's say I want to change the data types, because sometimes it might very well be possible that, let's say here, the target is an integer data type. But let's say I want the target to be a categorical variable. Right? Because the target is simply talking about whether this particular person had defaulted or not defaulted. So yes, no kind of a thing. So I would like to have it not as an integer. Let's say I want to have it as a category. Then I can very well try to change the data type by using this function called as type. So like this, I will utilize in this particular cell, I will try to change the data types of the various values that are there. If at all a number is wrongly coded as text, or text is wrongly coded as a, or an integer is wrongly coded as a float or something like this, I can very well think of changing the data types. Then I will quickly look at the descriptive statistics. Right, as we have already seen, the descriptive statistics is primarily to get 2 or 3 major patterns in the major identifications in the data. One, talking about are there any columns which are like zero variance kind of columns, where the standard deviation is 0. If the standard deviation is 0, it's a clear indication that all the values in that particular column are unique. There is no variability in that particular column. So you would take an action to delete that column from your data. That's one aspect. 2, are there any columns which are more of a serial number kind of columns, or some kind of a simple identifier kind of columns? So if I come across some such kind of columns, I would better knock out those columns from my model. That's the second thing. One is about zero variance. Possibly if I have to say what are the benefits from descriptive statistics apart from some additional. So one is ID related variables which are in a numerical form, drop them. Then zero variance related variables, if at all something are there, drop them. Then check for minimum and maximum values. Just see if there are some kind of erroneous values. Sometimes you may very well say, no, this value cannot have a minimum value of 0. Possibly when we are saying rate of interest, you may say, no, rate of interest, I don't think it can be 0. Possibly the minimum is 2% or something. I'm just giving. So in that case, what would happen? The minimum of 0 would be like a kind of a erroneous value for us. So we would try to write those kind of logics to typically see that the values which are beyond the acceptable maximum and minimum, they would typically go out. And the other thing, obviously, that we would be looking at is the distribution of the data in terms of primarily the skewness or kurtosis of the data. So in the regular descriptive statistics, you will not get these two, which means possibly you can very well look at the relationship between the mean and the median of the data. If they are more or less similar, then possibly we can comment on the possible normality in the data. But if they are very widely deviating, then we might very well think of scenarios where the data could be positively skewed or negatively skewed, or positively kurtic or negatively kurtic, which is a leptokurtic or platykurtic. And based on that, can I use some kind of linear models like linear regression or logistic regression directly for predicting purpose? Or should I think of some kind of non-linear models? Or should I think of transforming the non-normal data to normal, to near normal, transforming the non-normal data to near normal, so that I can go ahead and use some kind of a linear models on the top. So there are different kinds of scenarios that would come in. So right now my focus is primarily on these aspects, right? So because that is what is a preliminary data cleaning that we are doing. Obviously, based on the distribution and all, we may be doing something more that I would cover as a part of data preparation activity, which would be slightly before the model building, right? But before that, possibly these kind of data cleaning operations are very much required. So that is where we would look at the descriptive statistics, right? And similarly, I would also look at the descriptive statistics for the non-numerical variables also. Again, the intention in this exercise also is two things. One, look at the unique, right? How many unique values of each category are there? Two things here. If there is only one unique value for any category, even that would be like a zero variance kind of a column. So it's not worth to include that column in our model. So it's better to knock out that column from our model. So here I'm not seeing anything that is just one single unique value. All of them have at least two unique values. So on the face of it, I may not knock out any data point, any variable. But the second thing is possibly look at the distribution, especially when there are only two categories you can still make out here. Look at the distribution between the high frequency category and the next high frequency category or the lowest frequency, because if there are only two, then it is only high versus the low. So if we are seeing very few observations, let's say, I mean, I'm going for the very extreme. Let's say we don't have even 50 observations of the second category, then it's better to drop that column from the analysis, because most of the models may not be in a position to capture the generalization just with those 30, 40 observations when we are talking of a large volume of data. So in those cases, it would be more appropriate to drop those columns also from the model. So your descriptive statistics will give you some basic insights. Similarly, you can very well look at the number of unique. Here has 2019 only. So if that is the case, better to remove it. Right? Here, this is not 0, this is O. O is include the object. So what can be included and what can be excluded is what you can very well specify. Object is nothing but categorical. So if I say all, then both of them will be printed in one single table. But the thing is, for all the categorical variables, all would be shown as NaN, NaN, NaN. And for all numerical variables, these four rows would be shown as NaN. So it looks pretty odd in terms of the table. So that is the reason I typically separate the numerical description versus the categorical variable description. Then we are seeing number of unique columns. You could clearly see that the low near is having only one column, better drop it out. ID is having just, I mean, it's just an ID variable. It has no meaning in terms of the sequencing. So better drop it out. Whereas all others, I could see that there are minimum of 2 categories. So right now I may not be interested much in dropping them out. Then similarly, we can look at the skewness and kurtosis to understand. Right now, I'm not doing anything with the skewness and kurtosis. I'm only trying to understand how much the data is deviating from normality. I could see that a large number of variables, barring, let's say, the rate of interest and the interest rate spread, and to some extent the credit score, all other things are having some level of skewness. Possibly the term is having a negative skewness, and debt to income ratio is also having a negative skewness, whereas most of the other things are having a very high positive skewness. So when they are very highly positively skewed, it might very well be possible that when I'm using some kind of linear models in my modeling exercise, the results may not be the most appropriate kind of results. All right. So that is what we are trying to drive here. Similarly, I can also look at the kurtosis. The kurtosis is also giving a similar kind of a picture. It is talking about the thickness of the tailed observations. So here also the ideal number would have been a 0, somewhere around 0, because this is more like a excess kurtosis. So deviation from 0 is what is typically being looked at. I could see that there are some variables which are having a very high kurtosis values, like income, loan to value, property value. These are having very high levels of kurtosis, which is a clear indication that there are some very high extreme outliers that could be present in the data, right? So whereas some of them are negatively kurtosis, which is an indicator that possibly they have a very thinner tail, or it could be like a multi-peak kind of distributions as well. But overall, we see that there are a good number of variables in our data which are having very high levels of kurtosis. So which means combined together, most of my data is deviating from normality. We have looked at detailed descriptive statistics also in the last class, right? But primarily, if I look at this Jark-Bera p-value, if this Jark-Bera p-value is less than 0.05, I can very well say that my data is deviating from normality. I could clearly see that most of the variables, they are deviating from normality, which is a clear indication that possibly we will look at, please hold on to this point. We have made an inference right now saying that this data is deviating from normality. Now, what do we do to address it? Possibly let's hold on to this because I will talk about it during the topic on data preparation, which will be dealt before the machine learning, building the models, which would be another 3 to 4 sessions, 2 to 3 sessions down the lane. So right now, from the descriptive statistics, we are assessing that the data is deviating from normality. So that is one assessment that we get from the descriptive statistics. Now comes one more assessment where we try to, now in our data mostly we will have numerical variables and we'll have categorical variables. So in your exploratory data analysis, you will pick up the categorical variables first or numerical variables first and do some kind of a quick analysis on the top of them. In the numerical, we have already done. We have done a detailed descriptive statistics. And based on that, we have derived some insights from it. Similarly, in case of categorical, we have done some basic descriptive statistics for this also. But more than that, a slightly more detailed descriptive statistics for them is in terms of trying to understand how many observations are there in each category, right? How many observations are there in each category? So here, if you see for loan limit, we have 31 CF 135,000, whereas NCF is 9,000. So the intention primarily here is to see if there are any specific categories where one or more categories are having very low frequency, let's say less than 50. I would better think of removing those variables also from those variables or those observations to start with. I would like to remove those observations from the model because it may not add much of a value for me. But when I am removing those kind of observations, any observation that I remove from the model has to be highlighted as a limitation of the model. So what I mean by that is, probably if I remove, let's say, the land, so there are 33 observations in my data or 33 rows in my data where the secured by column is mentioned as land. Now, I would remove those 33 observations altogether. In that case, what typically happens is, right? In that case, what typically happens is, here there would be only home now. And if it is only one single column, it might become a kind of a zero variance column, and it might very well go for another round of deletion. So the column itself might get deleted. So especially in two variable column, only two categorical kind of columns, if you see that one category is having a very low frequency, which is, let's say, less than 50, it would so happen that it would be better to drop that column itself Because if you end up dropping the rows, it might very well become a zero variance column altogether. Now the next question comes, as our friend is asking, if the land is important in this data, then the next thing comes in terms of collecting a few more. There are 2-3 options here. One, collect a few more observations relating to the land. But many a times it might or might not be possible, because that's the entire data that is available with respect to the land related observation. In that case, sometimes, so these are all alternatives. Sometimes what I end up doing is I multiply that data, right? We have different mechanisms called minority oversampling or minority. We talk about oversampling and undersampling, right? So because of that, there is a mechanism to multiply the land values with some kind of a noise given to it, right? But these are all like manipulated things, right? Sometimes we may say that these are processes, but obviously they are slightly away from reality. So they are all subjected to some kind of bias in some form or the other, right? But if you still say that this variable is very important, my first choice would always be to go with collecting some additional data. But if it is not feasible, then probably you may have to you may have to do this kind of a oversampling or undersampling to typically address this particular concern. That way you will increase the sample size to 60 or 70 of these observations in a proportionate manner, and based on that you will still go ahead with the usage of this land data. Does that make sense, Dev? I'll talk about how to do oversampling and undersampling slightly later, right? But that is a way to go ahead. Okay, so we are now talking of, these are the basic things that we do before exposing the model. So this is all something that I'm talking of as an exploratory data analysis. You are trying to explore. Now we are handling the missing values, right? So right now I'm saying I'll handle the missing values, or I'll handle the erroneous values also before I handle the missing value. Now, what is that I'm saying? Just for the sake of argument here, let's say the rate of interest, I have seen in my descriptive statistics, I have seen that the minimum value for the rate of interest is 0. Right? The minimum value for the rate of interest is 0. And somewhere I'm saying possibly 0 is not acceptable. I just wanted to say wherever there is a 0, simply make it as a missing observation. So that's where I'm doing this erroneous entry. I'm treating that as an erroneous entry, and I am initially making those entries as blank. Anything that is less than or equal to 0, I'm simply saying make it as a blank value. Similarly, there are a few instances where income is also 0. So what I am also, it might very well be possible in the real world that people might have lost their job at the time of loan application. So I may not want to remove them altogether from the model. But here, just because I wanted to showcase how do we do this, I have just taken some couple of examples here. So one thing is, whichever is the value that I'm sensing as an erroneous value, by looking at the minimums and the maximums, I'm sensing that that particular category is an erroneous value. I would like to first make them as blank. So I'm initially converting them to blanks. Then similarly, any category with less than 50. So this is for the numerical variables. I'm putting all the numerical variables with some kind of a rules. So making all of those invalid values as blanks. And here also, I'm making all the invalid categories. As we talked about earlier, any category with less than 50 occurrences, especially when we talk about very large data. Possibly if I have small and medium sized data, then probably I can even adjust with around 30 records. But when we are talking of a very large data set, obviously even the 50 records would be a kind of a good, I mean, it may not be a kind of a sufficient thing. So if there are less than 50 occurrences, we are saying that we will replace them with blank. So now some new blanks have actually got. Earlier, the original data itself had a lot of missing values. But now there is a lot of new data also that we have gotten as a missing value because we have put some kind of rules or constraint. And based on that constraint, we have converted the actual values to missing values. And then we try to look at how many missing values are there. So I could see that there are a few columns like upfront charges where almost 40,000 missing values are there. Even these two like interest rate spread and rate of interest, where almost 36,000 missing values are there in the data. So sometimes when the number of missing values is very high like this, our total data is 1,48,000, and out of that almost 36 to 40,000 they are missing. So there could be various reasons associated with that missing. Possibly it might not be applicable, or possibly this data might be too old, for which that particular column would not have got captured long back, and we were capturing that column values only very recently. There could be different explanations to that, right? But what we are simply saying is, if a particular column is having too many missing values, like this case, 25%, 30%, sometimes it might very well be possible that right now I may not want to consider that column into my model at all, because the data availability for that column is always a big concern. So when the data is not promptly available, right, either I can very well say wherever the data is not available, right, possibly treat it as a missing value or something and do a separate analysis, right? Or better drop that column altogether, because then it is difficult to get the data when there are so many missing observations that are there corresponding to that better variable. Better drop that variable for the time being from your model. That variable might be a very important variable, right? But probably, I don't know, tomorrow when a new data is coming, whether that variable value will be available for that new data or not. If the variable value is not available for the new data, possibly your model may not do a good job for you. So that is where sometimes, especially when the number of missing values per a particular column is substantially large. Sometimes in some cases we talk about 80%, or in some cases we talk about 50%, etc. But anything more than 20-25% is always a serious concern, right? While some people argue that even if I omit those 39,000 records, I still have more than 1 lakh records. So still that could be analyzed. But possibly here the other take always is, when these 40,000 records are removed, it might very well be possible that there is some specific reason why those missing values would have come out. So it may not be completely random when it comes to missing values altogether. So if it is a kind of a random thing, that's fair enough. But sometimes there could be a very clear-cut pattern with respect to the missing observation. In those kind of cases, it would always be better to handle the columns rather than the rows. So there are a few columns where there is no missing value at all, whereas a few of them they actually became missing values because of our NA operation in the previous step, right? Wherever the total categorical count is less than 50, we said that particular variable could be converted. That particular category would be converted into a missing. So we got a few such kind of observations in that case. Now, what do you do with the missing value? So today we are also looking at what do we do with the missing value. So one case, drop the columns. So I'll say probably the first 3 columns. I'm just taking randomly. Don't take me seriously. Sometimes you may very well say that, no, I'll not drop all these 3 columns. Possibly I'll do something. So I am taking the scenario here that I would drop these 3 columns from the model. Right? It's also better that I drop the other 2 columns also, right? As we have been discussing. But of course, I'll not run it now because the data loading will take some time. I'll just put it in the code. You can run it later. So even these columns can very well be deleted, right? Then the other way is you try, if there is a kind of a missing value, you try to fill it with some constant of your choice. So here, the term, I'm saying if it is the missing value, try to replace it with a 90. That is something I may or may not be logical, but I'm trying to give. So when we are saying axis equal to 1, you're right. Axis equal to 1 refers to a column. So drop the column. Axis equal to 0 will refer to dropping a row. So the same drop function, but if you are putting axis equal to 1, then it is like search in the column and then drop it. And if you are saying axis equal to 0, search in the row and try to drop it. And here I am talking about if at all it's a missing value, replace it with some constant. Or if at all it's a missing value, replace it with some minimum value, maximum value, mean value, median value. So anything, right? You can very well replace it with some other value, some other function. So basically, this is what we are calling as imputing a constant value. So either 0, 90, something like that we typically say. Or here we are saying imputing with a function. So this function could be a minimum, maximum, mean, median kind of values. Or if it is a categorical variable, and if there are missing values in a categorical variable, now for example, we are talking about loan purpose. Loan purpose. Yeah, loan purpose has 134 missing value. Now, one way is I can drop them, but I wanted to show you different possibilities. That's the reason I just put it in the code with a hash. I didn't want to execute this line, but yes. So I will replace it with the mode of that particular class. category. Mode is the one that is coming with the maximum number of occurrences. So I would first compute under the loan purpose category, what is the variable that is coming out, the maximum number of occurrences I'll replace. Now that may not be a good way of imputation or replacement because I'm trying to manipulate the data. I may be going very much away from the reality in the data. Or the final option is drop. Drop the rows. X is equal to 0, you can drop the rows. So basically what is that you are doing? By doing this univariate exploratory data analysis, the first step. So this data analysis you keep doing again and again. But this univariate data analysis that you are doing here, it would really enable you to understand which variables are important in the basic stage. Right? What is that basic stage? It's a zero variance column. It's an ID variable. Or the number of observations, there are erroneous values. Number of observations in a particular category is fully dominant. Only one, majority of the observations, they belong to one single category. So you have many such kind of scenarios which can result in removal of the observations or removal of the variables. So that completes the univariate exploratory data analysis. Of course, there could be a few more activities that you might be doing, but this is what is a general univariate data analysis that you do. Then I would move on to the multivariate or typically the bivariate and then to the multivariate. So I think I see some questions. Let me just see. Yeah, in place equal to true is, so basically it overwrites the data. Right? If I don't put it, what will simply happen is it will print the data, but that value is not saved. So if I'm still using the bank as a variable later on, it would still be, it will not drop the rows. The blank rows are still available. But when I say in place equal to true, then it is like overwriting or replacing, as you rightly said. Okay, I think there is no Nikita, I think there is no significance of double quotes and single quote. Sometimes when I press double quotes, it come out as single quotes or vice versa. So it's just a kind of typing this thing, right? So you can go with one single convention. Both of them mean the same thing. Okay, so right now at this stage, they don't impact. Probably when you are working with some strings, there is a little bit of impact, which we will see in the context. Okay, any other questions on the univariate? Okay. So then we are going into the multivariate, taking two variables at a time. So in univariate, you are working with one single variable at a time. So in a multivariate, you are taking two or more variables. And our intention is to see, are they related? So sometimes I require the relations to be strong. Sometimes I don't require the relationships to be strong. So from that perspective, we would be typically seeing whether two or more variables are related. So that would help us in working out a little bit more better in our modeling exercise, right? So we are trying to see the kind of relationships that are existing between the multiple variables. So you can work with two variables at a time or more than two variables at a time. But the generic thing we see is we have three kinds of data with us, right? We have already talked about on a broader category, we have either categorical data and we have numerical data. We also have time, date, The other data formats, Boolean, etc. coming in. But the prominent data formats that we generally envisage are the numerical and categorical. Which means when you are doing multiple variables at a time, at least two variables to start with, you will see that both the variables could be numeric. If both the both the variables are numerical, what kind of preliminary analysis that you should be doing? What if one variable is numerical, the other variable is categorical? What if both of them are categorical? So that is one analysis that we can definitely do. Then within this itself, are we comparing both the variables which are feature variables? In that case, I don't want the relationship to be prominent. When I'm looking at the relationship between two feature variables only, I would always want that relationship to be as low as possible, which means I don't want a stronger relationship in that case. But when I am looking at a feature variable versus a target variable, I want the correlation to be higher. I want the relationship to be stronger between them, because that is what will help me deciding whether the feature variable is going to predict the target variable or something. So what can we do here? You see here, I am taking here I am first talking about categorical versus numerical. I'm talking about categorical versus numerical. You could see here, this is a very detailed analysis. So let's say I'm talking about feature here, right? Loan limit versus I'm taking all the numerical column. But of course, here we have dropped ID and loan here, but because I did not run the code, these are still showing up. But possibly if you run the code again, these two will not show off for you. So you could see this is between two features, because loan limit is one feature and all the numerical variables are other features. So you are going between one categorical variable and one numerical variable at a time. Now you could clearly see something. Possibly let's try to understand loan limit versus loan amount. So people who have NCF category of loan limit, possibly their loan amount, the mean loan amount is much higher. So possibly there is some kind of an interrelationship between the loan limit and loan amount. But I don't know with respect to the term whether there is any significant difference between these two groups. So possibly term and loan limit may not be related. Whereas the loan limit and property value, I could clearly see the mean values are extremely different. So you could see that there could be some level of relationship that is existing, some kind of association that is existing between the loan limit and loan amount, loan limit and property value, possibly loan limit and income. There is a decent level of association that is existing, but may not be with respect to the credit score, because both the numbers are looking pretty much the same. Even the loan to value ratio is not differing that much. We don't know, but small difference. But definitely debt to income ratio, I am not seeing too much of a difference. So there are only few variables which are significantly changing based on the loan limit. And similarly, now you can work out with the gender. I don't know, possibly the joint genders, joint account holders, they are getting a very high average loan amount. So possibly that is one more relationship that I can understand between the gender and the loan amount, possibly looking, the other three are in a similar zone, at least where the sex is not available, and in case of female, the average loan amount is more or less the same, but in case of joint account holders, looks like the average loan amount. So these are some of the kind of quick workarounds that you can very well see. So the term, especially here the average term, in case where the sex is not available, looks slightly on the lower side, but we don't know whether it is statistically significant or not. Same thing, the property value is much higher here compared to the other classes. Same thing goes with the income, possibly because it could be a joint income, right? So possibly the joint income for the joint account holders looks much on the higher side. There's not much of a significant difference in the credit score. Loan to value ratio, possibly a little bit higher amount of loans are taken by the males compared to the other categories. And debt to income ratio is more or less same, slightly higher for females. So some such kind of a quick insights, and wherever the results are more and more prominent, I think that is what will become the more important analysis that you inference that you make at this particular stage. Right? Similarly, approved, pre-approvals. You might very well see where the no pre-approval is there, the loan amount was much higher. Wherever the pre-approved loan was approved in advance, the overall loan amount was slightly lower. But the term is slightly the opposite way. So you could actually come out with various such kind of inference. Now, in all these cases, it becomes a feature to feature. So we really don't want too much of a significant association between the feature to feature. We want a very high association between feature and a target variable, but we generally don't want much of an association between a feature and a feature variable. So this is where sometimes we would clearly like to see whether this particular feature or feature numerical, categorical numerical kind of an association, would it have any serious impact on the overall accuracy of the model? So here, that is what now you look at the loan purpose, right? We are saying people with different purposes, but is there any clear-cut difference? Looks like you see the ones who have applied for the loan with a purpose P2, the average loan amount is much smaller compared to people who have applied loan with a purpose P4. So now what could very well happen is, it might very well come out that the loan purpose and the loan amount are very much connected. So they are not two different independent variables. There is some level of interdependency that is existing between the variables. Now, how can I directly use these two variables into my model? So that is what will become a kind of a question mark later on. So that is the reason when we are talking of those two variables being only the feature variables, we would like to have the degree of association between them to be as low as possible. Right? Probably here also you could see P2s are having a very low term, but P1s are having a slightly higher average term. Same thing goes with property value ranging from 41,000 to almost 60,000. The income also is ranging from 6,000 to almost 8,000. So these differences could be very much statistically significant. So possibly we may say loan purpose is one of the most important variables that is impacting the overall association with respect to the other variables. Right? You can also talk about, I'm not going much into them. Right? And now I'll go to the last variable, which is the target. Now, age-wise also we could see there are some age groups where the loan amounts taken, average loan amount taken is very much on the lower side. Possibly you could see here the people who are less than 25 and people who are greater than 74 and who are in the range of 65. So greater than 65, less than 25, greater than 65, we are clearly seeing that the average loan amounts taken by both these groups is very much on the lower side. Whereas all the other groups, they are considerably higher with respect to the loan amount. So possibly I may sense that there are two major categories of data, one with either too much of youngsters or too much of elderly people. So both of them, they are going for a moderate sized loan. Whereas the others who are in the middle age category, etc., they are going for a high end loan amount. And possibly you can very well do the interpretations accordingly. Right. So this is the kind of one thing. Now this is what I'm more into. Now this variable is more like target versus the numerical variable. Target is like a categorical variable here. Target is a categorical variable, and I am comparing across the two categories that are there. I want to compare the various numerical columns and see if there is any kind of an insight that I can draw. Now, a simple point that we are trying to say here is, if, for example, here between the target and the one of the variables, we would definitely want the relationship to be very significant. So if I look at here, the average loan amount for people who did not default versus who defaulted, the change in the average is pretty small. Right? Possibly it looks like, yeah, it looks like 19,000 difference is there. So it might be large as well. But possibly it is coming out that the people who did not default have taken a higher loan amount versus the people who defaulted. They have taken only a smaller loan amount. Possibly it might be a random error, or it might very well have some kind of a connected theory to the same. Similarly, you could see in terms of term, there is not much of a difference. In terms of property value, people who did not default have typically, so people who have purchased expensive properties, they did not default, but people who purchased smaller properties, there were more defaults. Now, the same thing is again income versus the target. People who did not default, the average income was 7,200. But for the people who have defaulted, the average income is 6,140. So this is very much fine, because people whose income levels are much lower, there are high chances that they would default on their loan. Credit score, we did not find much of a difference. Loan to value ratio, yes, someone who has taken a very high loan to value ratio possibly ended up into more of defaulting, whereas the other categories, they did not default because even their loan to value ratio was much smaller. Same thing goes with debt to income ratio. So the debt taken was higher in case of defaulting people versus lower in case of non-defaulting people. Right? So these are, so basically this is a numerical versus categorical. One categorical and one numerical variable. The only thing is we have collated all of them together, but every entry talks about one categorical variable versus one numerical variable. So this is one. Then I can look at both categorical variables. If both the variables are categorical. Now I want to see how many such kind of combinations are there. These are all the combinations that I can think of. Now what we say is, we do a simple cross-tabulation analysis. We can simply do a kind of a cross-validation wherein possibly I can very well simplify this analysis also, where I would look at only the target variable. Sometimes I may look at every pair, right? Possibly what is going to happen is look at every pair. Possibly I'll tell you how you understand this. So you see there's a lot of output that is printed. It all depends on how much you would like to analyze it. So feature versus feature first, then feature versus target. Now let's look at loan limit versus gender. Take this. Loan limit versus the gender. Now here you could see that, right, in the cross, so for the CF category, the highest is with the males. Very close is the joint, this thing, very closely behind. Then even for the sex not available, they are slightly lesser, and the lowest is the female. But in case of NCF, is the same proportion being maintained. So looks like joint is having the leadership here compared to the male. Male is pretty much closer. For the female, the value is much lower and sex not available in mid. So slight change in the sequencing. So we may not know whether these two variables are independent or there exists some level of interdependency between these two variables. Similarly, if you look at loan limit approved in advance versus the loan limit, 78-14, 4-2. Now the ratios are very widely different. 78-14 is almost like 6 times or 5.5 times, whereas here it is hardly double. So which means I can very well say that the proportions are not uniform across. So which is a clear indicator to start with is simply saying that these two variables are not completely independent. There might be some level of interdependency that is existing between the two variables. Similarly, you can talk about loan type and loan limit. 76, 11, and 5. But here I could see 5, 0.6, and 0.7. So here it looks like 0.7 is much higher than 0.6. Whereas here, I think it is 11, which is almost double to that of type 3, which is 0.05. So some changes are definitely there, right? 76 versus 11 is almost a 7 times kind of a number, whereas 0.051 divided by 0.006 is almost 9 times of that number. So some kind of dependency might very well exist, which can very well be ironed out by doing some kind of a statistical significance test. So here that statistical significance test that you might want to look at is typically the chi-square test. All right. Similarly, now you can very well compare all these things. You have a lot of things to really look at. So I want, because it's a comparison, feature to feature comparison, I want the relationships to be as low as possible, as weak as possible, right? Now I will look at with respect to the target variable. I want the relationships to be as high as possible. If they are not that high, possibly there is no point in progressing with the study. I can scrap this study here itself and I can simply move on. So let us see what is the impact of the target. This is the target. Loan limit versus the target. So possibly you could see the other way, 78 to 5 almost. 78 or this is 79 to 5 is almost like 16 times. So here it is 145 to 15. So this could be around 9 times. So might not be a big difference. Whereas if you are looking at target versus the female distribution, it looks like the joint has more number of non-defaulters compared to the males. Whereas here it looks like male and sex not available, they are having a higher proportion of defaulters compared to female and the joint account. So the non-defaulters versus the uh, gender, against the defaulters versus the gender, the numbers are slightly different. We may not say that it's a very significant difference, but definitely the proportions are not uniform. And similarly, you can also talk about the approved in advance. This ratio is somewhere close to 5, but this ratio is, I think, somewhere 6 plus or 7. So some small influence. Similarly, when I'm talking about loan type, 78 and 5. Whereas here it is 11, 3 and 1. Now, between these two, it's almost a 3 kind of a ratio. Whereas between these two, there is only a 4 kind of a ratio. Whereas here we are seeing almost a 8 or 9 kind of a ratio. So it looks like there is some impact. So they are not fully independent. There might be a little bit of interdependence of these variables on the target. So 21.7, 33.7 and 27.9. So here also it looks like the P3 is the highest, but probably P4 is the next, P1 is the next, and possibly P2 looking almost on the lower end. Right? So in some cases, you might very clearly see that the differences are pretty predominant clearly, whereas in some cases, we do not see the difference between the categories very predominant. So because of that, sometimes what could happen is some variables are more and more impacting, whereas some variables are not much impacting. So that's how this can actually help. Possibly when we discuss about something on feature selection at a later point, we would take the advantage of the results that we got here. There are some functions which automate this entire process as well. But definitely this mechanism can help us in terms of identifying which variables are key core variables to be included in the model and which variables do not increase any kind of efficiency. So this is one more, categorical versus categorical. The same thing, possibly we have established in a kind of a statistical test. Now in the statistical test, this is a typical cross-tabulation analysis. I hope all of you might be simply aware of that. Cross-tabulation analysis with a kind of a chi-square test being performed on the top of that. So a simple thing that we are saying is the two categorical variables that we have considered in every iteration, they are independent. So there is nothing where I can say the values of one variable are closely associated with the values of the other variable. So at least that thing is not clearly coming. I mean, that thing, so what we are saying is, as per the null hypothesis, there is no clear cut association, significantly strong association that is lying between the two variables. Whereas the alternate hypothesis says there is a significant association between the variables. So this is what is the null hypothesis. So and the alternate hypothesis, and we are trying to test that particular hypothesis altogether. So you could clearly see here the p-values of each of the tests are being published. So wherever we are seeing a p-value less than 0.05, I think in all the cases, at least up to here, the p-value is less than 0.05. So in all these cases, what we are saying is there is a significant statistical association between gender and loan limit, between approved in advance and loan limit, between loan type and loan limit. So I could clearly see that in all these variables, there is a very clear cut association between that variable and the loan limit. Whereas if I come here, I'm not seeing a p-value less than 0.05. So what we are saying, negative amortization and loan limit, they are not at all associated. Similarly, I have one more for greater than 0.05. Construction type and loan limit are not associated. Obviously, we have seen some time back that the construction type actually has one particular category to be removed, and because of that, it is typically made as a zero variate kind of a column, which would have simply got into a removal as well. Similarly, secured by and the loan amount also are having a similar kind of this thing. Now, yeah, total units versus the loan amount, slightly significant because it is 0.04 and it is still less than 0.05. But again, this credit type and loan limit, they are not at all correlated. So like that, you can observe sum of now region versus the loan limit, again, not correlated. Submission of application versus the loan limit, again, not. So you could see that there are a few variables where the relationship between them is not that significant, whereas a few set of variables where the relationship is heavily significant as well. So that is one more. Of course, let me look at the question. Can we reduce the number of units so that we can have good picture for interpretation? Oh, okay. You mean to say instead of too big a data set, I mean, you want to round it off, right? Yeah, of course. We'll put one line of code. So which would take care of that. Okay, then the last analysis that you might very well want to do is a kind of a correlation. Correlation is between two numericals. So we have handled all the three, one numerical and one categorical, two categorical, two numerical. So here also we could see between numerical values, right? Which of them are highly correlated? Property value and loan amount are highly correlated. Interest and loan amount are decently correlated, right? property value and loan to value are negatively correlated. Income and property value are positively correlated. So I could see only 4 or 5 such kind of pairs which are correlated, whereas all others are not that heavily correlated. That's one. Then the next analysis runs towards the identification of the outliers. Okay, possibly let me just hold on. Let me just hold on to this outliers. And the next that you would look at is visualization. I think we have already done all these visualizations. Again, you should look for 5 different kinds of visualization. One is univariate. Under the univariate category, there are 2 types of visualizations. One is a numerical variable, the other one is a categorical variable. So if it is a numerical variable, I can very well think of a histogram and possibly with some kind of density estimate, density plot or density estimate. And if it is a categorical variable, I can simply look at some kind of counting. So that is what is my univariate. So what did I do here? I picked up all my numerical columns and I try to plot the histogram, and along with that I will look at the density estimate. Now this will help me to understand what are the various values. Now you could see that with respect to this variable called a term, only 3 or 4 or 5 different values are there, and it looks like a very heavy left skewed kind of a data. Similarly, for the property value, I am seeing that it is more positively skewed. Income is also more positively skewed. Credit score looks more or less like a uniform distribution. Loan to value ratio again positively skewed. Right? Debt to income ratio is looking like a bit of negatively skewed. So what we are trying to say is, look at each numerical variable in any data set and try to generate this kind of graph. Similarly, I am taking categorical, right? Univariate categorical. I am simply talking about a simple count plot. So wherein I can clearly see that if one of the categories is too small, possibly it could suggest for a kind of a knockout. So you could see here again for all the categorical variables that are there, this kind of analysis is being generated. Possibly you could see here in respect to total units, only the 1 unit categories are too high in number. Target wise, we could see that there is a decent distribution between the variable and between the 2 target values. Similarly, I can talk about if I'm taking a multivariate analysis. Again, numerical to numerical, as we have already discussed, it's a correlation plot. And just for visualization, I can go for a heat map on the correlation chart. Whereas if it is a numerical and a categorical, the most common thing that I can think of is a box plot across the various categories. If I'm talking about categorical and categorical, I can very well think of between 2 categories, I can do a kind of a pairwise count plot. Whereas here I can also talk about the distribution related lot of advanced aspects as well. So going back to your data, here we are taking a kind of 2 columns at a time. You could see the major observation that we do with this is, are the proportions more or less looking uniform? So that is what is the major study. Possibly you could see here blue to orange to green is increasing, whereas here that pattern is not observed. So among the people who did not default versus the people who have defaulted, we see the proportions are slightly changed. Similarly, when you look at target versus the approval in advance, I don't know, this ratio might be more or less fine. Even this ratio might be fine. Target versus loan type. Target versus the loan purpose also looking pretty much fine. So sometimes what can happen is, here in all the plots that I'm making, I'm taking target as one particular important outcome. So based on that target as a variable, we are trying to see if the distribution of the values of those categories are in line with the target or not. You could see for every variable, we have captured something like this. You have to sit and typically look at. Now, if you look at this variable, construction type, only SB is there because the other category we have removed. So it's better to remove this column also rather than, but write it out in your scope document, because you have removed the data intentionally. So anywhere through a rule or something, if the data is removed, then that needs to be taken care into your writing. All right. Then similarly, all this, so we can generate one such kind. So when you actually start working on some other data set, these are all the dimensions that you would consider. Now here I have taken numerical versus categorical. So I take every numerical data and every categorical data, and we plot a box plot. So what we will do, we will look at the target. Right? So each one we are talking about with respect to the people who have defaulted versus the people who have not defaulted. So let's take one example here. Okay, let's take the first example. Okay, this is loan limit versus ID. I'm not much interested in the ID. ID and year I am not interested. We'll look at the loan amount. You see here, loan limit versus loan amount. We see here between CF and NCF category, you try to compare. Okay, here CF more or less looking same in default versus non-default. And even the NCF is looking more or less the same between default and non-default. How about here in case of gender? Possibly we find that the gender is also more or less uniform between the people who have defaulted versus non-default. Like that, what we say is, though you look at all the variables, feature to feature, we should not observe much of a difference. We should always see a kind of uniformity across. Whereas feature versus target, we definitely want them to be different so that they can be considered as a part of the model. So this is one more kind of a graph that you can end up plotting. All right. And finally, we can take two numerical columns. So we'll consider all the numerical columns. And we can simply either we can get the correlation as we have got earlier, or we can put that into a kind of a heat map, and we can really see which variables are positively correlated, which of them are negative, which are very high correlation, which are very low correlation. And the last chart that I would be interested in looking at is a QQ plot, the quintile plot, which would simply tell me to what extent does each of these columns conform to that of a normally distributed data. We have already seen the skewness, kurtosis, etc. Possibly here I could see to some extent the loan to value ratio is looking fine, but again we are seeing a lot of deviations toward the positive side, which could indicate a kind of a very high skewness in the data. So we don't see any specific variable to be more and more normally distributed. We have with a high correlation between them, because we have already seen earlier itself that the correlation value coefficients that are computed, they are significantly deviating from zero, right? So we have in this, these are all the things that we do. Then we generally also get into outlier understanding. We are not removing the outlier, but here we would look at the outlier, right? So I will stop this here for today. Possibly we will just look at this outliers in our next class. What are the different ways in which you can identify the univariate outliers? We will look at it in our next class. But typically after that, we will discuss a little bit about the concepts of machine learning. And after that, we will start discussing algorithm after the algorithm. So before we build any full-fledged machine learning model, we would also get into the aspect of data preparation, so that a model can be built more effectively and efficiently. So this is where I want to stop the session, but at the same time, I would share this file also with you. Yeah, tomorrow we have a session from 3:30 to 5:30 p.m. So on Saturdays, I have scheduled from 3:30 to 5:30 p.m. So we will I did not mention any time that I will cancel the class for Saturday. I did not mention it. I don't remember. I mean, I think I can take it tomorrow. I was only seeing if we can replace Saturday with a Sunday or vice versa. But I think most of the people would prefer a kind of a Saturday, so that, or I don't know. I mean, Saturday versus a Sunday, we have to take a call. Probably if I'm canceling on Saturday, then it would get extended. The course would get extended. So I'm not sure. So I think we will have to take a call. Possibly we will have some kind of a poll or something. So for tomorrow, we'll go ahead, right? But I don't know, Sunday being, I think everyone looking for having some kind of an off day. Possibly we don't want, and even Sunday is a working day for me, basically. So we'll see Saturday, and possibly otherwise we will add one extra weekday only rather than a Saturday if required. Yeah, tomorrow we will go with linear regression. So we'll have a session tomorrow, 3:30 to 5:30. So once I discuss about the outliers, I'll go for linear regression, basic aspects of linear regression. Before that, I discuss what is machine learning in a very broader perspective to start with. Okay. So I'll end this here. I'll share the sheet with you people. I think